just to introduce myself 30 seconds after my last introduction, I'm Jonathan Stringer from the Department of Mechanical Engineering, and basically I'm going to give you a talk today. It's going to give you an overview of mechanical engineering, and in particular some of the things we do, how the course of mechanical engineering, how it prepares you particularly for basically making things and innovative new things. And hopefully I'll explain a bit about that. So the first thing I'll say is, what is mechanical engineering? And basically mechanical engineering is really, it's about things that move. So if you're interested in designing things that in some way move, mechanical engineering really is the kind of field. And basically, when things move, you tend to need to use energy somehow. So if you think about a car as an example, obviously you put your fuel in, or you plug in your car these days if you have an electric car or a hybrid, and that takes the chemical energy of the fuel or the electrical energy of the battery, and it then converts that into motion, so the car is moving. So it's all about how efficiently we can use that. So we need to understand how we're converting energy from different forms, how we can do that as efficiently as possible. And it's also concerned with basically that can take on many things. So it can take on, like, how can I design an engine to literally burn the fuel as efficiently as possible? How can I eliminate friction that might lead to heat that I don't want? But it can also be, how can I design my mechanism that is moving to most efficiently use that information. And if you think about the things that effectively are moving, I gave the example of a car, but obviously there are many, many other examples. So things like aircraft, robots move, manufacturing production lines, they have lots of movement associated with them. And that's the kind of thing that mechanical engineers are involved with. And if you think about these things, basically most things move to an extent, or in a system they will move. And because of that, you find that mechanical engineering is probably the broadest of any of the engineering disciplines that you do, because you need to understand lots of different elements of what's going on effectively to properly help in your design of innovative products. So the kind of things that we need to know about in mechanical engineering. So I mentioned before about an engine. An engine converts some kind of chemical energy or electrical energy into motion, and that tends to be in the area of something like thermodynamics. Or if you imagine a combustion engine, that's obviously producing a lot of heat, and we're converting that heat, and we're looking at how that heat moves around. It also involves other areas, like how do materials behave when they're loaded, when they're stressed. So if you are designing something for carrying something, you need to make sure that it doesn't break. And understanding how loads are carried in materials and how materials can carry loads is a very important part of the design process. It's also worth considering things such as how systems move dynamically. So if you're designing a mechanism that involves, for example, the motion of a shaft or the motion of a wheel or such like, you need to understand how that wheel moves, and you need to be able to understand that to be able to design it properly. And then you can also move on to understanding how you make something, so the area of manufacturing. So once you've designed something, once you've done all your drawings, you've worked out, yes, that should work perfectly. If you're going to make it, if you're going to sell it, you need to work out how you're going to make it, and how if you need to work out whether you're making one of them or whether you're making 1 million of them, and you need to design something appropriate to how you're going to make it based upon that. And one of the key things when I was talking all the way through those, I was mentioning designing. And in a lot of ways, what mechanical engineering, indeed engineering, comes down to fundamentally is design. So you need to basically learn all this sort of engineering knowledge that you have with regards to mechanics of materials, or thermodynamics, or dynamics, or aerodynamics, or control systems, or manufacturing processes, and you apply that to make something. And you use all that knowledge to create a better design. And so design is a fundamental part of the mechanical engineering degree. And because of that, you have to learn what we would typically describe as soft skills. So as well as just the design process, chances are you'll be working with other people. So you need to know how to work in a team, how to communicate with other people, and various other sort of skills that are professional skills that will set you up well for a future role as a designer or as an engineer. so mechanical engineering in itself has been around for a very long time. And it's essentially been around since people have been designing things. You can argue mechanical engineering has been around since the invention of the wheel, however many years ago. However, there are another modern kind of influences on the mechanical engineering process, and some of these are based quite strongly around the use of sort of information technology. So if you think about, we have a lot of things associated with computer-aided engineering. So in the olden days, perhaps when we were calculating something, we would have, got out our equations and got out well, in those days, we would have got out our slide rule for anybody who's ever seen one of them in the audience. And then we would have, done our calculations, looked up our log tables and done screeds and screeds and screeds of numbers. Now, of course, we can get a computer to help us, which makes things a whole lot easier. And it's not just a case of using the computer as a calculator. We can also use computing to, and computer-aided engineering to model a more accurate kind of representation of what's going on in our system. And therefore, it can help us to refine our design. We also, there's a big element, and the talk following this, I believe, by Andrew at 9:30 is going to be about, specifically about a mechatronics engineering degree that we offer. And mechatronics is becoming more and more important because of the integration of electronics with mechanical systems. As you can imagine, if you're able to integrate electronics, for example, a sensor into a system, if you have a sensor that senses how much force is being applied, rather than you just having to make a design assumption and say, well, it's going to experience this load, you can actually measure it and perhaps keep track of what kind of forces, so you can have a better idea, for example, if your system is likely to work or not, and you can keep track of it. And then there are other big developments, and these are some of the things that sometimes get quite big news reports and things like that, which is some of the new materials and some of the new manufacturing processes that are coming about. So if you think about advanced materials, just by show of hands, how many people have heard of graphene? Yeah. How many people have ever seen graphene? How many people have ever used graphene? For the amount of press it gets, you'd think it was the most used material in the world, bar steel. But it's not actually used for very much, but that's because it's got so much potential, and it's only by studying it and understanding how it can be used, and that's where engineering comes in, that it will eventually get used in products. And then you have the areas of sort of micro-manufacturing and nano-manufacturing. So that's basically manufacturing at a very small scale. And a lot of this is related to how they make silicon technology. A lot of this, the manufacturing processes that are involved in making integrated circuits and microchips are being exploited so that we can use them in mechanical devices now. So we're able to make these things called MEMS, or micro-electromechanical devices, or systems, which is quite a strong area of research. And then the other area, which is certainly of interest to me, and that's in 3D printing or additive manufacturing. So when we talk about 3D printing and additive manufacturing, we often think of, you probably think of, there's sort of two viewpoints people see. They either see the sort of Star Trek replicator where it's like, all I have to do is have a file and I can press it and anything in the world will suddenly appear in front of me. Or you have people think, well, the only 3D printer I've seen is, it produced small plastic toys, effectively, that aren't really much use for anything except for looking pretty. However, it is some of the technologies used in 3D printing and additive manufacturing are now much more, becoming much more widespread. And, well, how many people have flown on either a Dreamliner or an Airbus A380? Yeah. With 3D printed parts, as you said, if you've ever seen them, you're probably thinking, that's not going to carry much load. That's not really very strong. I wouldn't want to trust my life to it. Would that be correct? There are 3D printed parts in both of those planes. So, but it's perfectly safe. Don't worry. There's a lot of quality control involved before they let it go on a plane, so don't worry. However, so as I said, an example of a mechanical system that shows how we integrate this was a car. So I mentioned some of this before. If you think about the evolution of a car, the earliest cars used steam engines. So all down here, and then eventually you develop the internal combustion engine, the gas engine, the gasoline engine, the diesel engine. One thing you note about that is, so they changed the type of engine, and that was to make it more efficient. So like I was talking before. So that would be very much a sort of thermodynamics and heat transfer problem. As they became more efficient, the cars are able to move faster. As they move faster, they realized that perhaps there were greater stresses acting on materials. There was more vibration. If you go along a road faster, you're going to feel the bumps more. So they started looking at the dynamics and the vibration of the thing to try and control it, to make it a more comfortable ride. If you went in one of the cars from about the turn of the 20th century, 19th century, and you tried to drive that at, say, 50 kilometers an hour, it would be a very interesting driving experience, and probably not one you'd appreciate for very long. So not only that, they improved the dynamics and vibration, and they realized if they wanted to go even faster, rather than having a design like at the beginning, which was basically a horse-drawn carriage with an engine and with no horses, they needed to do some aerodynamics. They needed to make it more streamlined, so it would go faster. And again, that cuts down on vibration. So you can see the shape of the car evolving because of design and improvement in the aerodynamics. And then as things go on, you start having people not, for example, in cars, lots more safety systems are introduced, so things like anti-lock braking systems or airbags. And then that's about when an airbag is deployed, it tends to, how an airbag is deployed basically has to sense its environment and work out if you are in a crash, because you don't want it to deploy when you're not, because then it's just a big balloon in your face and you can't really drive very well. So you have to have a detailed sensing and control system in there. And as things go on from the gasoline engine, we start moving to hybrid engines, electrical engines, and this is actually, the last one is actually a hydrogen-powered fuel cell car, which will not be on the road anytime soon commercially, but it's some of the way that these things are heading, and basically the complexity of this system and how you need to design it, and the role of the designer and the role of the mechanical engineer gets more and more sort of complex and important as this process goes on. But there are, of course, many other mechanical systems and things that mechanical engineers are involved with. So, for example, we've got yachts, we have drones. All of these involve elements of dynamics, fluid dynamics, materials, structures, and mechanics, and a control system. So we've got things that are, relatively exciting, like a jetpack or what have you. We also have things that you might consider relatively mundane, like a washing machine. If you think about a washing machine, it spins around at, up to probably 1,400 times per minute, RPM. And it's got to carry, good 5-10 kilos of your washing. And it's got to do that. And if it starts, they still do. Obviously, they vibrate a bit, but if it vibrates too much and it starts walking across your kitchen or your laundry, that's not going to be great. So you need to be able to design to make sure that doesn't happen. And then we have other things such as the bassinets, and one of the big ones, renewable energy. So you may think of renewable energy, electricity, that might be the realm of electrical engineering perhaps. But if you think about a wind turbine has to be a structure that's getting on for 50 meters, 100 meters tall. It's got to stay there, because generally speaking, they're in the middle of nowhere. You wouldn't really want one in your garden. So you probably want it somewhere out of sight, and you need to be able to, it needs to be reliable, and it needs to spin in the wind. It needs to cope with spinning at different speeds, depending on how it speeds, and you need to convert that energy into electricity as efficiently as possible. So it's an area that's very relevant for mechanical engineering. So what we do in our courses, we have to consider these problems as a whole. So if you're thinking about, as I said, a wind turbine, it's got to generate electricity with the turbine spinning, so you've got to consider the aerodynamics involved in that. You've got to consider the wear, so you'll probably have a gear set in there that will help translate that energy to power a turbine. You've got to consider how much is the gear set going to be worn down as it spins at different speeds depending on the winds. It's got to cope with a lot of forces, so you've got to make sure it doesn't, you don't want this thing to keel over in high winds. So you've got to make sure it's designed properly, and you probably want to design it so you don't have to go there every day to check on it. So you have to consider the whole sort of elements to it, and you have to do it, as I said, as efficiently as possible to generate electricity. And you find this with basically a number of items, and some of these items you might consider relatively mundane, and on the surface they are. But when you actually get down to what their working principle is and how they function, I personally find them quite astounding. So one example of that, an inkjet printer. Hands up if you've got an inkjet printer. Yeah. What do you use it for? What's it do? Would you say that's a pretty accurate description of what it does? Prints things out onto paper. Quite a mundane object. Doesn't really do much. Costs about $100 maybe, a bit more, a bit less. You can vary it. But if you actually think about what it does, I personally find it quite fascinating. What an inkjet printer actually does, rather than just print stuff onto paper, is it generates thousands to millions, depending on the printer, of identical droplets, and it puts them exactly where you want them and only where you want them. And it does this every second, without complaint, over and over again. The droplets are smaller than a human hair in width, and it only costs $100. How do they make something that does all these things so cheaply? And what it comes down to is by a lot of design and a lot of engineering. And the evolution of it is quite interesting to me. So first of all, with that, so how they generate droplets is actually a very similar mechanism to how a tap drips. Basically, a force is applied, in the case of a tap, gravity, to a fluid, and the fluid therefore moves and forms a droplet. However, the droplets are really small, so we can't actually rely on gravity, so we have to give it some other force. So in this case, we give it a little bit of electrical energy, which either shakes it a bit or heats it up a bit to generate our force. And if we do that, basically, we can generate a droplet. So this is just one print head. That droplet is around about 1/20th of a millimeter in diameter. And that image is actually taken of thousands of droplets superimposed on top of each other in the space of a few seconds. And it's only by understanding exactly what the fluid mechanics, how the fluid deforms, how heat is transferred, and the nature of the energies involved in the droplet generation process, that we can truly understand it. So rather than what would normally happen if we just force liquid through a hole, we get a spray, we're able to delicately control that and generate one single little droplet. And this droplet is always identical. And then the other thing, we can put them where they want them, so we think about positioning. And while it would be possible if we could say, like, well, if I want something to move that and I want something to move that, I'll just stick a motor on each one of them, and then they can all be controlled together. But the problem with that is that motors aren't cheap. However, making lots of complicated gear trains and linkage mechanisms so that you can move this motion and change the nature of the motion from one motor to control several things means that you can generate a complex series of things. So you have the paper being fed in, it moving on at certain times, the print head moving backwards and forwards. All of these things can happen with the power of just one motor, because you're able to design your mechanical system correctly. So it's only by understanding the sort of mechanics and the dynamics and the design process for this that you're able to basically make it much, much cheaper, so you can get your printer for $100. And then you have something that controls everything. So this is like the brain of the printer, effectively. So this basically tells when it should fire a drop, when it's moving. So you have this complex motion system that you've developed. You know you can develop droplets. You send it off to the computer and to the brain inside the system, and it tells it when to fire droplets. So this is all about understanding the manufacturing process itself and the control system as well. And what can you use it for? So certainly with design, you can print out your blueprints. So you spend all your time designing a three-dimensional model on your computer using computer-aided design software, and then you print everything out to 2D, which isn't particularly great. You'd much prefer to be able to print out in 3D. And so could you print out our 3D design? So the answer, as you may well be aware, is yes. And in fact, you can do it with exactly the same technology as the printer. Because the printer, as it is, prints out little droplets of, say, black ink or yellow ink or cyan or magenta ink. if you just change that, so effectively, rather than printing that out, it printed out super glue, and then on top of one layer of super glue, you printed another layer of super glue. On top of another layer, you printed another, and another, and another, and another. You'd end up with a three-dimensional object. And that's exactly some of the technology that's used in 3D printing. It's exactly the same as your little $100 printer you have at home. And the advantage of printing in 3D is, firstly, at the design stage of something, so you're trying to prototype, you don't have to worry about how something is going to be made. Effectively, as long as you design it appropriately, you can test how it's going to be made, and you can see it working in 3 dimensions. That means you can perhaps spot problems that you don't quite see on your design. You can handle it, you can see it from different angles. You can see, oh, potentially I can improve that maybe. So you're it's much faster in the design process. And you can also customize it. So I mentioned before about there are 3D printed parts on planes. Don't worry, it's not a piece of flimsy plastic. It's this. This is actually a bracket that's used on an Airbus A380, and you'll notice that it's got quite a complex structure. And basically this design has been optimized using computer-assisted engineering. They basically minimized the amount of weight and made it but still have the same strength by removing all the material they can from the design. And that means, obviously, if you can have a lighter part and it goes on the plane, your plane is more fuel efficient, so therefore there's less CO2 emissions, less greenhouse gas emissions, and there's less fuel consumption, so perhaps flying could be cheaper. So it's by using these technologies in the correct way, and going through the design process and understanding the manufacturing process, understanding the solid mechanics involved in how to make this, all the things that are covered in mechanical engineering, you're able to significantly save weight. So compared to the way it used to be made, this is roughly half the weight that it would have been beforehand. And that, if you multiply that over a lot of components over a plane, that's a significant cost saving and a significant environmental impact. So to encourage this on our class, we basically look at design and creativity and the whole process. So you look at how you can do hand calculations and how you can do builds. So for example, when you're in part 2, after you choose your specialization, we look at this, which is called the Warman Design and Build competition. So every year we have it's an Australasian-wide competition. So all the universities in Australia and New Zealand cover it, and basically you have to design a robot to finish an obstacle course and do a task. And we have an internal competition, and whoever wins that gets to go to the Australasian finals, which usually expenses paid to Sydney or Melbourne or something like that. So that's quite enjoyable. We also look at this design where we're basically trying to design a moving bridge, and that again, there's a lot of elements of that. So you've got the motion, you've got how you're going to design your system, but we also think about slightly bigger aspects. So this is a bridge that's going to be used by the public. So how are you going to design its use so it's going to be safe? How are you going to design it so that it lasts in its environment and it's considerate of it? And then in part 4, we start looking at prototyping. So here, this is just basically a speed competition for picking up cookies. And you have to design your cookie grabbing device. And so we get the students to make them, to prototype them, and then test them, and we sort of have a competition, see who can do the best. And that uses a lot of, so you can see on this one, you can see we get them to simulate exactly how it's going to move, to make sure they've got the right motion, and then we use those designs to 3D print and prototype our devices for testing. We also, in part 3, we look at this kind of modeling, so similar to that airplane part I saw. We learn similar skills here to try and minimize the amount of material that we use to gain a certain strength. And we also look at how you make things, so in this case in machining. And then as we go on in part 4, in the final year, we might have more involved projects. So these are typically in conjunction with a company. So this one we had a competition where we're looking at the design of a restraint system for a helicopter chair. And again, we were able to do testing and simulation and see which design able to come out best. While technically it's mechatronics, if you do go down to the display, you'll notice there's some big robot hands, and there's lots of small robot hands behind them. Those robot hands were actually from a design competition from last week that they did to design a grasping hand. So there's lots of sort of design sort of design and build things that go on in our course. So we have 2 degrees. I just mentioned mechatronics engineering, and of course this is mostly about mechanical engineering. Basically the key thing is there's teamwork is important. We tend to do a lot of group work. We work with each other, and that's basically to better prepare you for the real world. It's typical that you're going to work in groups when you're designing. So therefore, we feel it's appropriate that you should help develop those skills, which will improve your prospects in the future. So at the start of the course, you tend to have very core subjects, so you get a good solid knowledge foundation in your course. But then as the course moves on, certainly towards the end, you're able to select your courses so that you can tailor your degree to suit exactly what your interests are. So if you want to work very much in aerodynamics, you can select your courses associated with that. If you want to work with new materials and processing, you can select your courses to focus on that kind of area. With regards to career prospects, basically mechanical engineers are in demand. They work in lots of places. What you tend to find, one thing I will say, is because of the relatively broad base of mechanical engineering degree, mechanical engineers tend to be very good at managing other engineers because they know enough about all the other aspects to be able to understand and talk on their level. And they're also, as I said, very valued for their analytical problem-solving skills. The University of Mechanical Engineering is one of the top 100 universities by employer reputation in the world. So I would highly, there are good job prospects if you do come here. So basically, in conclusion, if you enjoy science, you're fascinated by how things work, if you have good analytical skills and good creative skills, and you like solving problems, engineers solve problems, and yeah, strong maths is handy, as with any engineering discipline. And if you like a sort of practical hands-on element in your design work, well, you sound like you make a great mechanical engineer, so please come join us. Okay, thank you very much. Are there any questions?